Okay, so we start statistics today, and that's chapter 8 of the textbook, Fundamental Sampling Distributions. Uh, well, we're going to study a population. Now, this population can be anything, but it has to be well defined. Say, for example, we take, say, college students. So our population can be college students. And we're going to study something like age, say, age of college students. So this is in fact a random variable from this population to R and X of some student, X of say student S1, say S1 is age of S1. Okay, so maybe we need that for say planning ahead and say how many colleges we need, how many say classes we need, something like that. I don't know, for some reason. Now, let's assume we do not have access to all college students. So what should we do? Well, that's what they do in statistics. We choose some samples from this population and study that. Now the process of this sampling, this is called sampling, the process is this. So let me erase this so I have enough space to discuss the process. So suppose you are a statistics professor and you want to study this X, the random variable that I defined. So you do this, you choose n students. So you choose n students from your class and you do something like this. So let's say this is student 1, this student 1, and then 2, and then 3, and dot. Okay. So this one, let's call it x1, then x2, x3, x. And this is like day 1. You send them out, day 2, and so on. So those students come back and bring you some numbers, which they have chosen some students at random, and they have asked their age, for example, and they give you some numbers. So this one would say like 17, this one like 18, this one 17, and this one 21, say something like that. Now you send them another day to find you, to bring you some more data. So this one brings 17, say 21, 19, say 22, something like that. And this continues until say day M, and then you stop. So it might be 19, say 25, and 26, say say 16, something like that. So that's what happens. Now, each one of them, this is important to understand. Each one of these students, and I wrote on top X, that X resembles the random variable X we have, but with some index. Each one of them is choosing at random a student and assigns to that student a number. So each one of them is like a random variable. So each student is like a random variable. It's like acting like a random variable. So each student picks one student from the population and in a sense assigns a number to that student. Yeah, you might say, okay, he doesn't assign anything, he asks, but okay, it's like assigning a number to that student. The second one, the third one, until the nth one. So these x's, the xi's, in fact, as you can see, are in fact they are not that x. They are not our own random variable x that we want to study. And in fact, they are. They are copies of the random variable that we want to study. So we have this sequence, or whatever you call it, x1, x2, xn. Each one is a random variable. In the population. And each one of them is a copy of x. A copy of x. And assuming that the students do not interfere, usually they don't, each one goes somewhere. Assuming that they don't interfere, we can also assume that xi's are independent. Okay. So with this sequence x1 up to xn is called the sample, in fact. So let me erase this and write down the definition of this from the textbook. So the sequence, which are in fact n students in your class, that is a sum. So here is the so it's definition, let x1, xn be random variables. And they are defined in the same population. Each having the same distribution as x. Okay, so that's what I said, each one is like a copy of x. So that's what we say, each one is a copy of x, and they are independent. They are also independent. They are also independent. Then this x1 up to xn is called a random sample of size n. Then this x1 xn is called a random sample of size n. Okay, of size n from the same distribution, from the distribution of x. Okay. So these xi's, as you see, I have written them in parentheses. It means that I mean that they are in fact that is like they have a joint distribution. So the joint distribution of these xi's has PDF. So PDF of the joint function of xi's is. So the PDF, we usually use f for that. It's f of x1, x2, xn. Since they are independent, we know that this splits into n functions. All of them are the same, in fact, all functions are the same. And f of x is the PDF of x. Okay. So that x1 up to xn is called a random sample. Its PDF is in fact fx1 times fx2 up to fxn, and each fx is a PDF of x, the same as PDF of x. Okay? So, now what really happens in practice is, well, if you can do this sampling many times, it's okay, but I mean, if you can send those students infinitely many times to go out and bring you some numbers, then that's fantastic. But most often that's not what you do. You just send them once to bring you numbers. Or you just send one person to do that. So it doesn't mean that they should be different students. It can be one student, except we should assume that when that a student picks one person from the population and asks, say, his age or her age, then when he picks another one, he picks that second one independently from the first one. Now, how that happens, well, let's hope that it happens. But if they are different people, then we can safely assume that it really happens. Okay. So we are given these x's, x1, x2, up to xn. And we want to study this. We want to study x, and we have some copies of x. And these copies are like machinery that can bring me data. And first thing that comes into mind, which, well, it has been around for a long time. So that is, in fact, the mean of this. So usually you ask for the mean. And mean makes a lot of sense. When you have a mean of something or some data, it gives you some kind of center of that data, where the center is, and the rest are on to the left or right or something like that. It depends on the dimension. So first thing you ask is mean. Now, what is mean of this thing? It's very simple. Mean is defined as x bar, and let me put n here, and that is 1 over n, sigma k from 1 to n, xk. Okay? So this is in fact the sum of some random variables. Each one of them is the same as the x that we have, and in practice what happens when those n students bring you some numbers as age of those college students, you find the say x bar of that. For example, let me draw the picture again. So suppose it's day 1, say day 1, and you have x1, x2, xn, and then we have x1. So this is like 17, 19, 19, and and then we have some X bar, which is like might be something like that. So then 19.5 is the value assigned to X bar. And remember, any function of random variables is a random variable. We didn't discuss this. In fact, that's the chapter before this one, chapter 7, which we didn't discuss. So any function of some random variables is a random variable. So what kind of function is this? In fact, this is, we're adding them. So it's like adding those. That's a function of those random variables. So X bar n itself is a random variable. Okay, now we want to see what distribution this one has. In fact, that's the first thing usually you study for any population. When you find the sample, to study that sample, you should know the distribution of this, or you assume the distribution. So let's see what we have here. This xn is the sum of some xi's, and all of them are copies of the same distribution. Well, if we go into the literature of probability and see what we need is this. Can the sum of some random variables with the same distribution have the same distribution or similar distribution? Or what is the distribution of that? What is the distribution of this sum? For this, we need a theorem, and I will write the theorem here, but without proof. The proof is beyond the scope of this class. So let me write down the theorem. First of all, whatever the distribution of X bar is, I can find its mean and its, say, variance. Okay, so how can I do that? So let's find mean of X bar. So before I say something, let me find E of X bar. So that's E of 1 over m and sigma xk, k from 1 to n. We know A is like a linear function, acts like a linear function, so then 1 over n comes out, and then you get this. So it is 1 over n sigma E of xk, and k from 1 to n. Okay, so if x, which all xk's are similar to x, if x has certain distribution, that distribution, let's assume that distribution has a finite mean. So if x's have some distribution with some mean and some variance, some mean and some variance, I don't know what the distribution is, whatever that is, assuming that the mu and sigma squared are finite, then E of xk is in fact mu. So this is 1 over n sigma k from 1 to n, and we have mu. Now this means add mu n times. So I have 1 over n times n mu, so that's also mu. So amazingly, the expected value or the mean of this X bar is mu. It's the same as the mean of this distribution. Okay? So let's write it here, and let me erase this and find the variance for you. So we found that X bar n, expected value of this is in fact mu. Okay. So let's find variance. So variance of x bar n, that's a variance of 1 over n sigma xj, k from 1 to n. I can write this in this form, because variance is not like that linear, but let me write it like this. I have x1 over n plus x2 over n, xn over n. Okay? Now each one of these is a random variable. I know, but it's divided by n, that's okay. Each one of these is a random variable, and we know these are independent, so these are independent random variables. So if we have independent random variables, variance acts like something like a linear, but it's not linear here. But variance of this kx is in fact k squared x. So each one of them will have 1 over n squared. So this equals 1 over n squared variance of x1 plus 1 over n squared variance of x2 up to the last one, 1 over n squared variance of xn. Now we know each one of them, each variance is given here. This sigma squared is variance of this distribution, right? Xi's have a variance sigma squared. So all of them are sigma squared. So I have 1 over n squared, and I have n sigma squared here. So this will be sigma squared over n. So we have found the variance of this, in fact, is sigma squared over n. So let me erase this. We didn't need the distribution to find these two. Those are, in fact, properties of expected value and variance. But now, the theorem, in fact, is not this. This is part of the theorem. The theorem is that if the distribution is normal, so if xi, each one of them is normal with mean mu and variance sigma squared, then x bar n is normal with this expected value and this variance. Okay. In fact, you might say, so what did we do here? What did we prove? Because this is very easy. That's not the theorem. Yeah, the theorem is in fact this: that if you have normal here, then when you add them, you will get normal. So the part of the theorem, which I said is beyond the scope of this course, is in fact this: when you add normal distributions, the sum of normal distributions is in itself a normal distribution. Well, I have divided by n, that's okay, well, that's also a normal distribution. So that is the part which needs more mathematics, say, to prove. Anyway, so the sum of normal distributions is a normal distribution. And we found expected value and variance of that, and that's it. So x bar n is this. Now, since we are doing this, let's also find the distribution of this sum. The distribution of the sum is also important. Although we might say, okay, it's just divided by n. So yeah, it should be something like this. So we can also find, if I prove that, if I say, so this is, the proof is the same. Let's say y is in fact sigma k from 1 to n xk. Okay. Then what is e of y? E of y is e of x1, x2, x3, blah, 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 blah. So we have n of them. So that is n mu. And what is variance of y? Variance of y, since there is no n here, I'm not dividing it by anything. So that's variance of x1 plus variance of x2 and so on. So that is in fact n sigma squared. And since I said the sum of normal distributions is a normal distribution, so if xi is, well, I erase that, if this is normal, mu sigma squared, then y is normal with n mu and n sigma squared. Okay, so now before I continue, there is a terminology which is used and it's called statistic. So statistic is in fact any function of some random variable. So we can say that x bar n is some statistic related to the population I'm studying. This is also another statistic that's like adding some of them. Anyway, so when we define a statistic, we usually the first thing we find is some distribution for that statistic. Okay. So we found that x bar n has where is the right? So let me write it here somewhere so we know that x bar n has this distribution. That's the normal with mu and sigma squared over n. Okay, so well, there are other statistics that we might consider. In fact, if you use some, say, package like R, for example, some program like R, it also can give you other statistic. So another statistic is what? You have heard that. So this is mean. You have heard that. The other one is median, right? So another statistic, median and mode. Okay. I don't think we need any of those, but when you do practical statistics, say if I want to see something regarding, get some idea on the grade of my students, I look at both the mean and the median and mode. In fact, the system gives me all three of them. So mean is that, and the median is in fact the middle of the data. So for median, you just look at the data. If you have, say, an odd number and you have put them in order, then you pick the middle one. If you have an even number, you pick the two middle ones and find the average of that. Mode means what? Well, both of them are applied to discrete data, and mode is also which one of them is you see more often. So, for example, if in a class I see like a grade of say 72, and say 20 students have grade 72 and the rest are other grades, then 72 will be the mode, because more students have gotten 72. Well, anyway, so those are in fact some, it gives you some idea and in practical statistics. Now, we usually use this one and we need the distribution for x bar. And look at this. This, I'm assuming that it has a continuous distribution. So I'm not using anything else. I'm using continuous distribution. Although you might say, okay, what population is continuous? If it's population of anything in the universe, there are like 10 to power 22, say, particles or whatever in the universe. So that's finite. It's too much, but it's fine. So, but as I said, and I say it again, assuming that it is continuous helps us a lot. So that continuous model is a great help because then I can use calculus and differentiation, integration, and such and such. Oh. So, well, let me. Now, I will post something on D12 for you, some lecture notes. So we will be using R. So you need to download R Studio and say, for example, in R Studio, when you have a set of data, you want to find the mean of that. Well, it's very simple. Just say mean of this. So, and it will give you the mean. If you need standard deviation, which is sigma, so mean is that x bar, and standard deviation is sigma. So sigma, in fact, is square root of variance. And remember, variance is, in fact, positive. So that's the square root of variance. Okay. So you have mean and standard deviation. You can find it. So, for example, mean is just mean of some data. If I remember correctly, so mean of something. And this one, I think it's like SD or something like that. SD. So you can Google that and see what comment to use to find mean and standard deviation. Now, you can use other packages if you can use pandas, for example. Or Python. If you know how to do that, that's also very popular. And anyway, so well, both of them are free, so you can download and use them. So if you have used Python, you might want to use pandas, and you can find a lot of information on how to use pandas on Python or R. Okay, let me give you an example of. Can I find an example from? Well, so this is a nice example in the book. Okay, yeah. So, well, it says that. So let's say example. So it says like a manufacturing company. Produces engines. Okay. So the age of the engines has normal distribution. With mean, say, 59 and standard deviation. Okay? An individual buys at random, say, 25 items. What is the probability that these engines last more than 16 years? So that is some nice problem. So we have a company that produces some engines, and the age of the engine has normal distribution with mean 15 and standard deviation 4. So for us, the population is the engines. So population is the engines, all engines, and this individual at random chooses 25. So that 25 is like the XIs. So X1, 2, 3, 4, 5. So each one of them, he chooses each one and say, so he has 25 engines, 1, 2, 3, ... 1. Well, I mean, you're predicting here. Otherwise, you have to wait many, many years to see when they die. Whatever, you're predicting. So each one of them is like a student that a random variable, or that stat students picks from the population of students. So this is like you go on there. So it's like you have 25 students, each one picks an engine at random. Then you ask this question: what is the probability that the average age of these is bigger than 16? Okay, so if this is x1, x2, x25, right, then we don't know what this one is. So this one might last 17 years, this one 21 years, this one say 5 years, this one say 22 years, something like that. Okay, so then we don't know this. As I said, if you want to see that, you have to wait many, many years and see what happens. But we want to predict. Okay, so in that situation that I told you, I can say let's predict. So when you send your stat students to find out age of some n students, you can ask the question: what's the probability that the average age of those students that they pick is bigger than 17? Even before they return and give you some numbers. This is like that. This is like that. So we want to predict something. We want to predict and see what if the average of the ages of the ages of these, which we don't know how much that is bigger than 16. Okay, so let's put this in context that we usually have. So let me 25. Let me write some numbers here before I erase this thing. So I have a mean is 15, sigma is 4, and n is 25. Anything else? Oh, no, n is 25 and this is 16 years. And 16 years. Okay, so we're gonna. The question is this. So find the probability that x bar 25 is bigger than 16. So that's what we want to find. Probability that x bar 25 is bigger than 16. Okay, so we can answer this if we know the distribution of x bar. That's why we need distribution. That's why we defined, or we found distribution of x bar. And one reason that we choose normal distribution is because of this. In fact, there are other distributions that have similar property, but normal distribution is the best. And we will see because of another, in fact, theorem which I will discuss. So this one, so x bar 25 is in fact normal, we know from the theorem. Its mu is 15, and its variance is 4 squared sigma squared over n. So that's 4 squared over 25. And that is sigma is 4, we have sigma squared over n, and that is sigma squared over 25. So that is distribution of my me. So I have to find this. So this is in fact P of x bar 25 bigger than 16. If I use the PDF of that distribution, the normal distribution, that is 1 over square root of 2 pi sigma, which is in fact, if this is variance, so this is sigma squared of this. So the sigma of this is in fact 4 over 5, right? That's variance. Variance is sigma squared. So square root of 2 pi times 4 over 5, integral from 16 to infinity e to power minus, on top I have, say, y minus mu 15 squared, this is squared, and over 2 sigma squared. 2 times sigma squared, which is 16 over 25, and dy. Okay? So you can use like your calculator, for example, or you can use R to find this probability. In R, every probability, every distribution has some name, like normal. It's just normal, N-O-R-M. And so it is like this. It's P of something x, mu, and sigma. And the name of that distribution comes here. So P norm is probability. So P norm of, say, 16, mu is 15, and sigma is 4 over 5, is probability that x bar 25 is less than or equal to 16, right? So probability is in fact from negative infinity to this point, right? So, but I need the tail of this thing, so this probability in fact is P of x bar 25 bigger than 16 is 1 minus this P of P norm of 16 and 15 and 4 of P norm. And that will give you the probability that you are looking for. Okay. Well, this one was, it has an assumption. It has an assumption that the xi's have normal distribution. What if we don't know the distribution? Which usually we don't. Yeah, we can assume that it has such and such distribution, but sometimes we don't know that. Then what? And sometimes, we are given some population, and we want to choose some samples from the population. By studying those samples, we want to find these parameters. These are called parameters of this distribution. Some distributions have 2 parameters like this one. Some have 1, like exponential distribution has lambda. That's just 1. This one has 2. Okay, so what if we don't know anything? We don't know the distribution. What happens? And suppose we are able to find, say, mu and sigma. If you have the population in this era, it's very simple. If you are looking at, say, students in the country, it might be easy to find all of them. Not easy, but anyway. So you might go state by state and find college students and the names and ask for the age and look at the age and things like that. So what I'm trying to say is that you can find mu and you can find sigma, but you don't know anything else. You just know these 2 numbers, which are not hard to find, and then what? Then what can we say? Now, for that mu, this is what happens. So we have another theorem. I just write the theorem 2. This is called central limit theorem. CLT. That's known by CLT. And it's saying this, that x bar n, let's write another random variable. This is my random variable Zn, which is x bar n minus mu over sigma over square root of n. This mu statistic, which is a statistic, is a random variable itself, because this is the random variable. These are constants. And n is changing. Central limit theorem says that this, in fact, approaches some z in distribution. That part is, in fact, not easy to prove, and it needs a lot more mathematics, even at a higher level, graduate level, to prove that this, in fact, in the limit gives me a random variable in distribution. So you see, if you find the distribution of it, somehow that distribution should converge to the distribution of that z. And z has distribution normal 0. And that is amazing. That is amazing. No matter what distribution I have for the xi,